A peer-reviewed paper just landed in one of astronomy's top journals, and the result it reports is this. One galaxy observed by the James Webb Space Telescope appears to be older than the universe itself, at a statistical confidence of 4.7 sigma. That's a 1 in a million chance of being a fluke, the same threshold particle physicists use to claim a discovery, and the researchers aren't saying this might be an error. They're saying this is what the data shows within their models, and they can't make it go away. Let's talk about what's actually going on here. The paper was published on February 10, 2026, in Monthly Notices of the Royal Astronomical Society. That's not some fringe outlet. That's one of the gold standard journals in astrophysics. The authors are Martín López-Corredoira and C.M. Gutiérrez, both at the Instituto de Astrofísica de Canarias in Spain. What they did was analyze 31 galaxies observed by JWST at extreme distances. These galaxies exist at what astronomers call redshift 6 to 10, and redshift is essentially a cosmic timestamp. The higher the number, the further back in time you're looking. At their average redshift of about 7.3, the universe under our standard model of cosmology was roughly 700 million years old. That's it. 700 million years since the Big Bang. The universe was a toddler. Now here's the problem. When they modeled the light from these galaxies, broke it apart, figured out what kind of stars were inside them and how old those stars were, the average age came back at about 610 million years, plus or minus 310 million years at 95% confidence. Just sit with those two numbers for a second. The universe is 700 million years old. The stars inside these galaxies are on average 610 million years old. That leaves about 90 million years between the Big Bang and the moment these stars started forming. 90 million years to go from a hot soup of particles to organized galaxies pumping out stars. That's not a lot of runway, but that's the average. The individual cases are where things get really uncomfortable. The galaxy that's causing the most noise is called JD's 105323. It sits at redshift 6.9. At that redshift, the universe was about 800 million years old. The best fit for the age of the old stellar population inside this galaxy came back at roughly 9.5 billion years. 9.5 billion. In a universe that was 800 million years old. That doesn't just push against the limits of our cosmological model, it blows right past them. And the authors ran the statistics. The probability that this galaxy is actually younger than the universe at that epoch within their modeling framework is less than 1 in a million, that 4.7 sigma number. So either something is very wrong with how we estimate the ages of stars inside distant galaxies, or something is very wrong with the timeline of the universe, or maybe both. Every option is interesting. Let me give you some context on why this matters, because this didn't come out of nowhere. Since JWST turned on and started sending back data in mid-2022, it has been finding things in the early universe that nobody predicted. Within weeks of the first deep field images, astronomers were spotting galaxy candidates at incredibly high redshifts. Objects that appeared to exist just 300 to 400 million years after the Big Bang. Brighter, bigger, and more abundant than any model had predicted. The big shock came when Ivo Labbé and colleagues identified 13 massive galaxy candidates in Sears survey data. Some of these things appeared to contain as many stars as the modern Milky Way, crammed into a space 30 times smaller. Erica Nelson, one of the co-authors, had a pretty memorable reaction. She just called it bananas. You don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. And a Yale astronomer, Peter Van Dockum, put it another way. He said it was like looking at rocks from the earliest times in Earth's history and finding fossils of fully formed animals. That analogy is perfect because it captures the fundamental weirdness. You're looking at the baby photos of the universe, and instead of finding blurry smudges of barely formed stuff, you're finding what look like fully grown adults. Now, the initial reaction in the astronomy community went through a pretty recognizable arc. First came shock, then came the corrections, because some of these early candidates turned out to be wrong. The most dramatic example was an object called Sears 93316. Its photometric redshift suggested it was at redshift 16. That would have made it insanely far back in time. Then they got a spectrum, actual detailed light fingerprinting, and it turned out to be at redshift 4.9, a dusty starburst galaxy whose emission lines happen to mimic what a primordial galaxy would look like. Not ancient, just tricky. Another team from the Canadian NIRIS survey reanalyzed objects similar to Labe's original sample and found none of them were actually that massive or old. And a study by Catherine Chorowski showed that when you removed a specific type of object called little red dots, compact things that probably host active black holes whose light was inflating the apparent mass estimates, the remaining galaxies were broadly consistent with our standard model. So there was this wave of relief. The universe isn't broken after all. We were just fooled by some tricky objects. But then new discoveries kept appearing, and the corrections couldn't explain all of them. Jade's GSZ 14.0 was spectroscopically confirmed at redshift 14.32. That's roughly 290 million years after the Big Bang, and it was surprisingly bright, 1,600 light-years across, with detectable oxygen. Then in May 2025, another galaxy called MUMZ 14 pushed the record even further to redshift 14.44, about 280 million years after the Big Bang, and in March 2025, astronomers detected Lyman alpha emission at redshift 13.05. One of the researchers on that team, Kevin Hainline, said flatly, "We really should not have found a galaxy like this." Meanwhile, other teams were finding what they called red monsters, ultramassive galaxies at redshift 5 to 6 that were forming roughly 1,000 solar masses worth of stars per year, with baryon conversion efficiency around 50%. For comparison, typical efficiency today is maybe 10 to 20%. So the current state of play, even before this new February 2026 paper, was something like this. The most extreme impossible galaxy claims had been deflated, but the universe still had roughly twice as many massive early galaxies as our models predicted. As Chorowski herself put it, we are still seeing more galaxies than predicted, although none of them are so massive that they break the universe. And then López-Corredoira drops this paper, and it shifts the conversation in a specific way. See, most of the earlier debate was about mass. How did galaxies get so massive so early? Michael Boylan-Colchin, who did the most rigorous stress test of this question, showed that reproducing the most extreme candidates would require essentially converting 100% of all available matter into stars. That's physically impossible, but it was still a question about efficiency. How fast did stuff come together? López-Corredoira's paper asks a different question. Not how massive are these galaxies, but how old are the actual stars inside them? That's more fundamental because it directly challenges the timeline. A galaxy with stars averaging 600 million years old in a universe that's only 700 million years old doesn't just need efficient star formation, it needs stars that started forming almost immediately after the Big Bang. There's essentially no buffer. So how did they figure out the ages of these stars? This is important because it's also where the biggest criticisms come in. The main technique is called spectral energy distribution fitting. Basically, you take all the light from a galaxy across many different wavelengths, from ultraviolet through infrared, and you compare it to computer models of what different combinations of stars, dust, gas, and other stuff would produce. You try thousands or millions of combinations and find the one that best matches what you're seeing. The key feature they were looking for is something called a Balmer break. When a galaxy has a lot of older stars, there's a characteristic jump in the light spectrum around 4,000 angstroms in the rest frame. Younger galaxies don't have this feature, so a strong Balmer break combined with the Lyman alpha break from intergalactic hydrogen absorption creates a V-shaped pattern in the spectrum that points toward mature stellar populations. The new paper is actually an improvement on an earlier study by the same team from 2024. That first paper looked at only 13 galaxies and got even more extreme ages, 900 million to 2.4 billion years, in a universe that was only 600 million years old. The new analysis uses more data, 31 galaxies instead of 13, JWST mid-infrared data for 15 of them, and actual spectra from NIR spec for 13. They also fixed a coding error from the earlier paper where emission lines weren't being properly accounted for. And they added explicit modeling of active galactic nucleus contributions and intergalactic absorption from neutral hydrogen during the ionization era. The result is that the new ages are significantly lower than the old paper. So in a sense, the better data made the problem smaller, but it didn't make it disappear. And for that one galaxy, JD's 105323, the tension is still extreme. Now here's where we need to be honest about the weaknesses, because there are real ones. The biggest issue with the most dramatic result, that 4.7 Sigma galaxy, is brutally simple. There's no spectrum for it. The extreme significance comes entirely from photometry, which is essentially brightness measurements through different filters, combined with model assumptions. A proper spectrum, where you actually split the light into fine detail and can see individual absorption and emission features, would nail down the age much more reliably, or potentially blow the whole thing up. And the method itself, this spectral energy distribution fitting, has a well-known problem. It's degenerate. That means different combinations of age, dust, metallicity, and star formation history can produce very similar-looking light. An old galaxy with little dust can look a lot like a young galaxy buried in a lot of dust. A review by the astrophysicist Charlie Conroy summarized it pretty bluntly. There is little consensus on how accurate light-weighted or mass-weighted ages from these fits actually are, especially for complex systems. Then there's the dust question specifically. López-Corredoira's team assumes that the young stars in these galaxies shouldn't see much less dust than the old stars, because that would be physically hard to justify. But there's actually a very standard model in galaxy physics called the two-component dust model, where young stars that are still inside their birth clouds experience extra dust obscuration that older stars don't. If you allow that, the V-shaped spectrum becomes much easier to explain with young, heavily embedded star-forming regions instead of old stellar populations. And there's an even wilder alternative. A 2025 paper by Inayoshi and Maialino showed that you don't even need old stars at all to produce a Balmer break. Very dense clumps of neutral gas surrounding a young, growing black hole can absorb light below the Balmer limit in a way that mimics what old stars would do. So what looks like an ancient stellar population might actually be a gas filter around a baby supermassive black hole. That's a very different physical picture. Most of these 31 galaxies are classified as little red dots. LRDs. These are compact, red objects that JWST has been finding all over the early universe, and they've become one of the most debated classes of astronomical object in years. A study by Del Kuchevsky found that over 80% of these things show signs of gas moving at more than 1,000 kilometers per second, which is evidence for active black holes at their centers, not just massive collections of old stars. And depending on how much you attribute to the black hole versus the stars, mass estimates for individual LRDs can vary by a factor of 100. 100. Same object, different model assumptions, wildly different answer. By late 2025, a study by Ruskov and colleagues in Nature concluded that LRDs are young supermassive black holes shrouded in dense cocoons of ionized gas, with true black hole masses about 100 times lower than previous estimates. NASA itself put out a press release titled, "Webb finds early galaxies weren't too big for their britches after all." So there's a strong case that at least some of what looks like impossible old stars in the early universe is really active black holes messing with the light. But López-Corredoira and Gutiérrez did test for AGN contamination. They added an active galactic nucleus template to their models with its own dust extinction parameter, and concluded that on average, the AGN contribution to the reddest wavelengths was small, less than 25% at 95% confidence. So they're not ignoring the issue. They're arguing it doesn't fully explain what they're seeing. And this is exactly where the scientific tension lives. Two groups of serious researchers can look at very similar data and reach opposite conclusions, because the answer hinges on details that are incredibly hard to observe directly. How is the dust distributed? Is the red light coming from old stars or from a shrouded black hole? What's the real star formation history? These are not questions you can answer with a few broadband filter measurements in a model. Now, there's something else worth knowing about this paper and its important context. The lead author, Martín López-Corredoira, is not a newcomer. He has over 210 publications. He holds dual PhDs in physics and philosophy. He's a permanent staff astrophysicist at one of Spain's most prestigious observatories. But he's also spent much of his career arguing that our standard model of cosmology has problems. He's written papers and books specifically critiquing lambda CDM. His earlier version of this study was co-authored with Fulvio Melia, the leading proponent of an alternative cosmological model called R sub h equals CT, in which the universe at redshift 8 would be about 1,500 million years old instead of 600. That would conveniently dissolve the age tension entirely. None of this invalidates the science. The paper passed peer review at a top journal. The data is real. The analysis is detailed. But it matters that this is a researcher who has been looking for cracks in the standard model for decades and has now found data consistent with that position. It's the kind of thing that warrants extra scrutiny, not dismissal, but scrutiny. And to be fair, López-Corredoira himself calls the result provisional. He writes explicitly that there may be other uncertainties in the models, and further research is needed to confirm it. That's more measured than the headlines suggest. So what does the mainstream think? Stephen Finkelstein, who runs the Sears survey that produced much of this data, has been pretty clear. The bottom line is there is no crisis in terms of the standard model of cosmology. Anytime you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out. Boylan Colchin, who did the most careful stress tests, agrees. Most people would put their money on the astrophysical explanation right now, meaning the issue is probably with how we model stars and galaxies, not with the age of the universe. And Nashwan Sabti from Johns Hopkins made an interesting point. If cosmology were broken, we should see some sign of that in the Hubble data. We don't. There are also specific solutions being proposed that don't require any new physics at all. Enhanced star formation efficiency in the early universe. Bursty star formation histories that make galaxies temporarily overluminous. Top-heavy initial mass functions, where the early universe produced more massive stars than today. Feedback-free starbursts in extremely dense early conditions. And one study by Cullen and colleagues in 2025 showed that current data can be reproduced by assuming ever younger stellar populations consistent with formation at redshift 15, requiring no changes to anything exotic. And there's even a connection to another big open problem in cosmology, the Hubble tension, the disagreement between different measurements of how fast the universe is expanding. A class of models called early dark energy, which were proposed to fix the Hubble tension, can also match JWST's observations of bright early galaxies. Two problems, potentially one solution, all within the framework of tweaking the standard model rather than throwing it out. But let's be real about something. Tweaking is not nothing. If the early universe really did form stars 2 to 5 times more efficiently than anything we've seen in the nearby universe, that's a major update to our understanding of galaxy physics. If initial mass functions were different in the early cosmos, that changes how we interpret basically every galaxy we've ever observed. These aren't minor footnotes, they're big revisions. And there's a really interesting historical echo here. In the early 1990s, cosmology faced almost the exact same crisis. The ages of globular clusters, the oldest collections of stars we know, were estimated at 14 to 16 billion years. But the age of the universe, calculated from the expansion rate and assuming a matter-dominated cosmos, came out to only about 10 to 13 billion years. Stars older than the universe. Sound familiar? That crisis wasn't resolved by improving the stellar models, though those did get revised. It was resolved by discovering an entirely new component of the universe. Dark energy, the accelerating expansion driven by the cosmological constant, pushed the age of the universe up to 13.8 billion years, comfortably older than any known star. It was arguably the most important cosmological discovery in decades, and it came directly from an age crisis that most people initially assumed would be resolved by better astrophysics. So the question today is, are we in a 1990s repeat? Is this age tension the first rumbling of something fundamentally new about the universe? Or is it a modeling issue that will evaporate once we get better spectra and better understanding of what's going on inside these weird little red dots? Honestly, most of the evidence points toward the boring answer. The models need work. The data is ambiguous. The objects are complicated. One really important galaxy doesn't even have a spectrum yet, and the broader population of early JWST galaxies has mostly been explained by normal astrophysical processes, just pushed to extremes we didn't expect. But most of the evidence is not all of the evidence. There are still roughly twice as many massive early galaxies as models predict. Record-breaking objects keep showing up at redshifts above 14, and an entire new class of astronomical object, these little red dots, hundreds of them scattered across the early cosmos, still don't have a consensus explanation 3 years after their discovery. The mystery is real. The question is whether it's a mystery about how stars and galaxies work or a mystery about the universe itself. And that's a question that might get answered pretty soon, because the single observation that could settle the most extreme claim in this paper is straightforward: a deep near-spec spectrum of JD's 105323. If someone points JWST at that galaxy and gets a clean, detailed readout of its light, we'll be able to see exactly what's producing the Balmer break. Old stars, young dusty stars, a shrouded black hole, or something nobody's thought of yet. One spectrum. That's all it would take to either confirm or destroy the most dramatic finding in the paper. Until then, we're in that uncomfortable middle ground where the data is suggestive but not conclusive. The stakes are enormous, but the uncertainties are real, and the universe is doing what it always does, refusing to make things easy for us. Think about what we're actually dealing with here. Light that left these galaxies over 13 billion years ago. Photons that have been traveling since the universe was in its first few percent of existence. They arrive at a telescope floating at a point 1.5 million kilometers from Earth, get collected by a gold-coated mirror 6.5 meters across, and land on a detector so sensitive it can pick up the heat of a bumblebee on the moon. And from those photons, we're trying to figure out whether the stars inside a galaxy that's been dead for eons were born 50 million years after the Big Bang or 500 million years. The fact that we can even have this argument is kind of absurd. The fact that the argument might change our understanding of the cosmos is something else entirely. Maybe this paper's wrong. Maybe the ages are inflated by dust or black holes or some modeling assumption nobody's caught yet. That's the most likely outcome. But there's a non-zero chance, and López-Corredoira would argue it's not that small, that what we're seeing is the first crack in a timeline we've taken for granted, that the universe didn't give galaxies 700 million years to form. It gave them something else, more time or a different kind of physics, or conditions at the dawn of everything that we haven't figured out yet. Cosmology has been wrong before, and the last time galaxies appeared older than the universe, the resolution reshaped everything we thought we knew. If you want more of the latest science that's actually challenging what we thought was settled, there's always another discovery waiting.